All right. So we are going to be looking at what we call correlation. And a simple correlation coefficient is a measure of the degree of strength and direction of linear relationship between two variables. And don't forget, we talked about our variables x and variables x and y the other time. Now, if you look at your regression, talk about x as the independent variable, y as the dependent variable. Here, we are not really concerned about which is dependent on or which is not dependent. Our concern is the relationship. All right. So, looking at this, we are trying to see if as one variable increases, maybe the other one also increases, or as one variable decreases, the other one also decreases. And if you remember, when we looked at um, what we called a regression line, we said it could happen in a number of ways. All right. Now, so we could have slope is positive, slope is negative. All right. So in this case, although we may not look at the regression line, we have a coefficient by which we can measure relationships. Now, you may see a trend, the stuff is going, maybe the plot you have is going like upward or coming downward, but the coefficient that we obtain okay, so the correlation coefficient helps us to be able to measure the strength and direction of the relationship. Now, it doesn't mean that the two variables now, like one of them has to be independent and the other one has to be one of them has to be dependent and the other one has to be independent. No, that's not what we're saying. You may look for the correlation coefficient between two independent variables, all right? But there is something we call coefficient of variation. That one, we'll be looking at that later on. It has to do with a dependent variable and an independent variable. All right, so let's start with the correlation coefficient. Now, we've talked about the definition. Now we can look at how to represent this. We do that by using what we call rho, a Greek alphabet called rho. Looks something like this. You can browse it. That's the name here, rho. So called rho in Greek. This is not is, please. Sorry about that. Now this is for the population. So when you calculate your correlation coefficient from the population directly, you are going to call that rho. But if you obtain it from a sample taken from the population, you represent that with R. Now, a correlation coefficient of -1 means that there is a negative relationship, a perfectly negative relationship, whereas a correlation coefficient of +1 means that there is a perfect positive relationship. So perfect negative relationship, perfect positive relationship. But the closer it is to 1, maybe -1 for instance, then the stronger the relationship negatively. But the closer it is to +1, the stronger the relationship positively. So the relationship may be positive, may be negative. What am I saying? You may have it to be maybe like, for instance, 0.7. So from 0.7 to like, this is positive now, to when it is positive, I mean, plus 0.7 to +1 is very strong. And in like manner, strongly positive, I mean in this case, strongly positive. But from -0.7 to -1, strongly negative. All right, so now it could be any other thing. Perhaps it may be 0.6, 0.6 something, 0. Yes, they also show some relationship between the variables. when you have those kind of coefficients, but it's not as strong as when you have it to be this way. All right, now going forward, we need to know these assumptions about the correlation coefficient. The first one is the sample is a random one. So the sample you take that you want to calculate your what we call R now, the sample correlation coefficient, the sample must be random. All right, the data pairs fall on a straight line and are measured on an interval ratio level. That means you cannot use something that is categorical. So for instance, category A, category B, you can't do anything that has to do with correlation on that kind of data set. But if you have metrics like 2 points, just remember your continuous variable. Remember we talked about continuous and discrete variables. So when the variable is continuous, then you can look for what we're talking about here, the correlation coefficient. You can look for that. Now the variables have a joint normal distribution. So we are looking at two variables, don't forget, and we had looked at joint distributions. Now, so we are assuming that the kind of distribution you're considering here is normal, and then we are considering that there's a joint distribution between the two variables that you want to obtain a correlation coefficient for. All right, so you should note the following. Number one, when correlation is perfect, +1 or -1, all the points lie on a straight line. That means you're going to have something like this. This line is not straight enough. Okay, something like this. Yeah, so a very straight line. Now, correlation is positive. That means it's direct. When the slope of a regression line is positive, obviously, you may not even need to look for the correlation coefficient before you are able to guess what the correlation between two variables will be if you plot the regression graph. So if you plot it and you have something like the line is going upward, it may not be perfect. It means there is a positive relationship. But if in any case it is perfect, then definitely that's looking more like something that is deterministic. It's not random. That means, for instance, your y equals to mx plus c, no error. So that's going to be a perfect line if you draw that for any kind of, so whatever m may be, whatever c may be. All right, whatever you plot, if you use not this one now, there's an error here, so definitely you don't expect all points to be on a straight line. But I'm saying that if you do that for this particular equation, no error is there. Definitely you have all points falling on a straight line. All right, so in case you don't really understand what I'm saying is that, for instance, you have these ones now falling, they're not on a straight line, not on one line, let me say it that way. If you plot this equation here, then you are going to have something that looks like this. The line is always going to be straight, or you may have a line that looks something like this. It may be falling, but it will be straight. It will be a straight line going upward or coming downward. Now, you know that already. That is the case for y equals to mx plus c. But for the data that you have, you will not have everything falling on a straight line. So it may look something like this, or even something not going upward like this. But when you see it going upward, it tends upward. Some points may be here, some points may be here, some other ones here, some other ones here, some other ones here, like that. But predominantly you find out that it's going in a straight line. Then it means that there is a positive relationship between the two variables. Now, going back to our correlation, we are saying that when the correlation is perfect, +1 or -1, all the points lie on a straight line. That means there's no error, and that is what you you obtain when you do y equals to mx plus c. But when you do a regression, a random data, a data that was taken randomly from the population, you are not going to have a perfect line. You're not going to have a straight line. So except you are correlating that variable with itself. So if you do correlation of x and x, definitely you should have a straight line. All right. But if you do correlation of x and y and you obtain the data from a random process, you cannot have a perfect correlation. At best, you may have something like 0.9 something, but you cannot have one. All right, please take note of that. We'll go on. Correlation is positive or direct when the slope of the regression line is positive. Now, when we saw that, I said that when the slope is positive, it goes upward. When the slope is negative, it comes downward. Yes, that's true. That is very much true. And we are looking at that now here. So when the slope is positive, the correlation is positive. That means the correlation, when the slope is positive, the correlation is positive. That means the correlation is direct. When the slope is negative, when the slope is negative, the correlation is negative. So correlation is negative when the slope is negative, not positive here, please. Negative, meaning that as one of the values, should have off here. Okay. Sorry. As the values of one variable increases, the values of the other increases as well. Okay. Okay. Now, meaning that as the values of one variable increases, the values of the other variable increase as well. Meaning that as the values of one variable increases, the values of the other variable decreases. Okay, as the values of one variable decreases, the values of the other variable decreases as well. So that's what we are saying here. And the absence of a pattern, whether increment or decrement, means there is no correlation. In this case, the correlation coefficient is 0. And that's what you are going to find in this case. So you will not find any correlation between the two, because you're just going to have, and you may not be able to obtain any meaningful thing here for the correlation coefficient. All right. Now, but when there is a pattern, you can see it to be either going up or coming down, going up positive, coming down negative. Okay, let's say it this way. The correlation may be positive. It means that as one variable increases, the other variable also increases in quantity. This is what we are saying. Maybe the first variable is x, the second one is y. If x is 2, y is maybe 4. If x is 3, y is maybe 5. If x is 8, y is maybe, you may have 2 here. In practice, you may have 2 here, for instance, but predominantly it's increasing. But at some point, you may not really see an increment or something. So, but in when you do y equals to mx plus c, which is mathematical, the case is actually not like that. So most times you have a formula already that when you substitute a particular value of x, you get a direct y, but does not apply to data in reality. It doesn't apply exactly the same way, because sometimes you may have something like this. It's increasing, but there are some points that are offset, or rather that are not increasing or not following the pattern. So many points may lie along the straight line here. You may have them, but some of them because of what I just said now, some of them may lie somewhere here, another one may lie somewhere here, but predominantly, the majority of data points may lie along your line that is increasing, that is going up, that is having a movement upward, an upward trend. All right, so that's what we are trying to talk about here. In that case, we are done with, okay, we have looked at that. So the absence of a pattern, when we say the absence of a pattern, we are saying that the data set may just be in such a way that everything is just lying maybe somewhat like this, or it may even be in straight lines. Sometimes you just find out that you don't really see anything that makes sense, like maybe an upward trend or a downward trend. Those are the two we look for. That's when there is a correlation between, and we're talking about linear relationship between the two variables. All right, that being said, let's move on. Now, how do we obtain an estimate for the correlation we're talking about? Now, how do we obtain an estimate for the correlation coefficient? Now, don't forget that we could obtain it from the population, but when the population is large, we may not be able to obtain all. We may not be able to get all possible values. So what do? We can obtain it from a sample. So maybe a population of 2 million people, we may just take maybe 100,000 or 50,000, and we may obtain the correlation coefficient for them. Now that will be a lot cheaper than obtaining it for 2 million people. Now, okay, that will be cheaper than obtaining data from 2 million people. So if you just obtain for 50,000. Now, but we are looking at the sample correlation coefficient here, and the definition, or rather the formula for it, is what you are seeing on the board. It doesn't look so far from, it looks somewhat similar to the regression coefficient. One of the coefficients we looked for, or rather the coefficient we looked for, the coefficient of X, when we were doing the regression stuff. Well, you may see some semblance, but they are not the same anyway. Now, we go on to look at it. You may do it this way, or just simply obtain the covariance of X and Y, and then the variance of X separately, the variance of Y separately, and then you just find the square root here. So you finish your mathematical work, and then whatever mathematics you have done, if you have done it correctly, you obtain what you get here. Because actually this was obtained from here. All right, so we go on. There is something we call the coefficient of determination. I talked about it earlier on, and it is the square of the correlation coefficient we obtain using any of these two, and it tells the amount of variation in the dependent variable that is explained by the independent variable. I was saying I was going to come back to this the other time. This is the only time when you need to, when you're doing your correlation, you need to be sure that before this can have any meaning, you need to be sure that you have a dependent variable and an independent variable. That's when you can interpret this correctly. If not, if the two are dependent variables, then your definition may not really, or rather the interpretation of your coefficient of determination may not really make any, may not really make any sense. So be mindful of that. You use it because look at the definition here. It tells, or rather what it's interpreted as, it tells the amount of variation in the dependent variable that is explained by the independent variable. So if you have two independent variables and you are looking for the coefficient of the correlation coefficient between them, you don't need to talk about the coefficient of determination. All right. Now the test of significance of the estimate of the correlation coefficient is also important. This has to do with hypothesis testing. So let me quickly say that if at any point in time you may not understand everything about this, but the main thing here is to be able to uh, do find out if what you have obtained is significant or not. Meaning that what you have obtained using this, you want to see if what you have obtained. You want to see if it is actually not due to chance, because it may be due to chance. You just obtained it, but it doesn't really represent the population value, or you cannot generalize what you have obtained from the sample based what you have obtained based on the sample. You can't generalize it on the population. And our desire when we do estimation, because we know we have a rule, I mean that's the population correlation coefficient, and we are obtaining is a correlation coefficient, a sample correlation coefficient called R. Now we want to generalize based on the value we obtained from the sample. We want to generalize it on the population, so that though we obtain for 50,000 people, for instance, we want to say, okay, now we are not limiting our result to the 50,000 people, but we'll talk about the result as though we did it for the 2 million people. That's our concern. So generalization is the concern here. We want to generalize the result. And there is no way we can do that if what we have obtained is not significant. And it is not significant when we do not reject H naught. But it is significant when we reject H naught and accept H1. That's what it means. Now look at this. We are saying rho is equal to 0. So if we accept H naught, that means we do not reject H naught. Then it means that we are saying that what we obtained has no meaning. All right. So please be aware of that. Be mindful of that. We move on. So when we do that, we need to obtain a test statistic called T calculated. It will be, so N here is the number of observations you have. R is the coefficient, the correlation coefficient. So you square it here. You can obtain this, and we move on. Now, after obtaining this, the intention is to compare this value with the table value. There is a table called the T table, and it can be used to obtain standard values from the T distribution. So the T thing here that you are seeing here is a distribution, actually a distribution called student T distribution. Now, when we have done that and we obtain the value, we compare. If what we calculated is greater than the value from the table, then we reject H naught, this one. We reject H naught, called the null hypothesis. But if it is less than, then we do not reject H naught. So that means that if we reject H naught, what we obtained is generalizable. It is not due to chance if we reject H naught. But if we do not reject H naught, then it means that it is not generalizable. It means that it is due to chance. That means we cannot take the result we obtained from the data we got from the 50,000 people. We cannot generalize it on the 2 million. We cannot use it on the population. We can't say, okay, it applies also to the population. So we just have to stop with the 50,000 people. All right, but if we reject this, it's generalizable, so we can extend the result we got here, that it also applies to the 2 million people. All right, so that's that about that. Now, let's see, what can we do with our correlation? Now, let's look at an example. Obtain the correlation coefficient for weight and calorie intake using the data on patients admitted in PYZ hospital below. Now, we have this data, and what we need to do is to obtain some sums, the sums that were written in the formula, and So it's not looking very different from what we did when we wanted to obtain our regression coefficients, except that this guy, y square, was not there. All right, so going back, you see that now we had y, x, xy, and x square. But this time around, we're having y square also. So that's the difference between the two. Now we obtain all the sums, and then we go on, we move on. You already know that you just, to obtain this one, you sum everything here, you get summation y. You sum everything straight down, you get summation x. So you multiply this, I mean y by x, 60 times 2, 120, 45 times 1.3, 58.5. And you do that for all the other columns, and you sum them straight down, then you get the value here. You sum this one, okay, you square your x here, 2 square gives you 4, 1.3 square gives you 1.69, and like that, and then you sum everything, and then you get summation x square. You do something likewise, okay, you do likewise for y square, and you get your value there, and then you substitute the values, and you get 0.7049, and then you square your correlation coefficient to get the coefficient of determination, becomes 0.4969, so 0.4969. Then you interpret your R this way. Now R can be interpreted thus, since R is 0.7049, there is a strong positive relationship between weight and calorie intake. Now, if it were to be 0.6, for instance, you're going to say there's a relationship, not so strong anyway, but there's still a relationship, and a positive one. But if this were to be negative 0.7049, you would have said there is a strong negative relationship. So don't forget 0.7 going upward to 1 measures a strong relationship. It's strong then. Now we go to R square, the coefficient of determination. It can be interpreted by saying 49.69%, that's just multiplying what you have here by 100. So that converts it to percentage. So 49.69% of the variation in weight, that is the dependent variable now, is explained by calorie intake. Calorie intake is the independent variable. Or you may just say 49.69% of the variation in weight, the dependent variable, is explained by the fitted linear regression line. All right. Now we move on to hypothesis testing about correlation coefficient. Now substituting all your values, n is 5, don't forget, and then we have all of your R is 0.049. So when you do that, you get 2.4267, which is approximately 2.427. I did that because of what we're going to be looking at next. So let's look at the T table. Now the T table is a table of T distribution. We call it student T distribution. And what do we do here? It is our intention to obtain a value from this, but you need to understand two important things about the T distribution. Number one is the fact that there is a level of significance. So you have T alpha, level of significance called alpha, and there is, okay, what we call the degree of freedom called, I may use N, but in the table it's written DF. That means shortened form of degree of freedom. So degree of freedom. All right, so everybody likes to be free. All right, now, but this time we're talking about the degree of freedom for the T table. So looking at that, for instance, I want to obtain it for our example, we will be obtaining it for alpha equals to 0.5 and n is 5. Don't forget n is 5 is coming from the fact that we have 5 observations. I mean 5 observations. That's the sample size, just 5 for x and y. Now we look at that 0. So we're looking for t 0.05, comma, the degree of freedom now, and the degree of freedom is we said is 5. So let's look at that. How do we go about that? We are doing a two-tail test. Be aware of that. The reason is because in the H1 side, you can check, you see that when we're giving alternative hypothesis, we said rho is not equal to 0. So not equal to is a two-sided test. If we had greater than alone, it would have been one-sided. That means we would need to be looking at our values along this line. If it is one-sided, if it is less than, it's one-sided also. If it's greater than, it's one-sided. But once it's not equal to, is a two-tail test, and it means we need to look at the one below, two-tail. So we're looking along this line. All right. Now, so looking at that, we are looking at that for the two-tail test now. So 0.05 is here, and what's the degree of freedom? The degree of freedom is 5, so it's here. So you can draw a line with your, you just slide with your hand. If you draw a line on your table, you may destroy the table. The table may not be usable again. So the lines intersect here. So that gives us 2.571. All right, so you can obtain it for any value. Usually we use alpha equal to 0.5, but in some cases, some other persons for some reasons may be interested in maybe 0. Any, it may be this, maybe this, maybe this, maybe anyone, but we usually use 0.05, and for academic purpose, it's usually 0.05 also. All right, so we've gotten our value to be 2.571. So that's our t value. Okay, so 3 figures after the point, or 3 digits rather. But we have 4 here, so I made it 3. All right, so to facilitate a good comparison. Now, a good comparison. Now you put this, you see now that 2.427 is less than 2.571. That means what we calculated is less than what we obtained from the table. And in that case, we cannot reject H0 because our rule said that we only reject H0 if what we calculated is greater than what we found in the table. So that means we cannot reject H0. All right. I put this in. So, okay, we conclude that the correlation coefficient is not significantly different from 0. That means you cannot generalize what you have obtained here on the population. You just need to stop with the sample. You just talk about the sample. You cannot generalize the result you obtained here on the population. Now, okay, what I put in, what I've underlined can be taken out. You may not like to write yours like this in case it looks confusing, but I like to write mine like this because it helps to facilitate comparison easily. But if in any way you're confused or you don't like this one, you may just write, therefore, since t calculated is less than, so the other stuff here, this one, you will now say we do not reject H0. We conclude that, so you may leave yours like this, but I prefer mine, but you can't use the two. You just write one. So now we are done with that, and that will be all for this lesson. Thank you.